Hey everybody, so this is going to be a little bit of a review for collisions and a little bit of practice for collisions. So it's important to understand that the equations for collisions come from the ideas of the conservation of momentum. So your initial momentum has to be equal to your final momentum when all of your forces are internal to your system or that there are no external forces acting on your system. Okay, so the change in momentum before is equal to the change in momentum after. So we understand this when we look at collisions. And we noticed two different types of collisions. One was elastic, the other was inelastic. So inelastic collisions are when things combine together, there is heat generated, and that equation can be seen right at the bottom here, the second one. All right, so your masses combine together in one object. Elastic collisions are when things collide, but the momentum gets transferred from one thing to another, and that there is no joining or fusing or deformation of your objects. So a good example of elastic collisions would be like with pool balls. Okay, they just collide, they separate out, and they move on their merry way with a different type of velocity. Inelastic collisions would be like with car crashes and the cars sticking together, or with train cars fusing together with the little hook and moving on with one type of velocity. So it's important to understand how you identify what collision you're working with. When you're asked to solve for one final velocity, like total for your system, it's important to recognize that that's when you solve for inelastic collision equations. When you are asked to solve for one type of velocity for one object, that's an elastic collision equation. You can also be asked to solve for the initial stuff, but we're going to see that in just a second. So let's get started with question 1. So Millie is standing using frictionless roller skates while catching a 2.5 kilogram medicine ball moving with a velocity of 14.5 meters per second. Millie has a mass of 45.8 kilograms. What is the final velocity of Millie? So if we were to really visualize this, we can see Millie on roller skates and he's about to catch a medicine ball. So what type of collision is this? Well, these two masses are going to come together when Millie catches this medicine ball. So this would be an example of an inelastic collision equation. So let's write that down, inelastic. And our inelastic collision can be written with the equation of m1 times v1 plus m2 v2. And this is all initial before the collision. Then the equal sign, this is when the collision happens. And what happens is our masses combine into one system object, and we are left with a final velocity for that object. Okay, so let's identify what we are given in the problem. Okay, so M1, I'm just going to call it the medicine ball because it's the first mass that we're given. It's just that simple. All right, and we are given that the medicine ball is moving with a velocity of 14.5 meters per second towards Millie. So this is going to be 14.5 meters per second for the initial velocity of medicine ball, or M1 in this case. Millie has a mass of 45.8 kilograms. And let's just assume that Millie is just chilling on his roller skates. He's not moving at all. And I'm assuming that because we aren't given an initial velocity for Millie. So I'm going to call V2 as 0 meters per second. So we have all of the information that we need in order to solve. All we need to do now is plug it in. All right, so we have 2.5 kilograms times 14.5 meters per second plus 5.8 times 0 is equal to our masses combined times VF. And this velocity final is what we are trying to solve for. So what is the final velocity for Millie and this medicine ball object system? Okay, so all we have to do now is do the math. So 2.5 times 14.5. And that's going to give us 36.25 kilogram meters per second. plus 45.8 times 0, which is going to give us 0. And this is going to be equal to our object masses combined. So this is going to be 48.3 kilograms. And in order to solve for your final momentum, you need this final velocity, which we need to solve for. All right, so our initial momentum is 36.25 kilogram meters per second. And again, this all stems from the conservation of momentum. So our initial momentum has to be equal to our final momentum. Again, not the velocities and not the masses in this case, but the products of your velocities and the masses. So let's go ahead and continue to solve for our final velocity. All right, so I'm just rewriting so it looks a little bit neater. All right, so VF is going to be equal to 36.25 divided by 48.3. So this is going to be equal to 0.75 meters per second. Okay. All right, so this next one's a bit harder to identify, but astronaut Mark Lee is 84 kilograms and is at rest outside of the Space Shuttle Discovery to test the safer device. Mark fires a thruster that expels 0.035 kilograms of hot gas at 875 meters per second. What is the velocity of Mark after firing the thruster? So this is actually an elastic collision. So elastic here. All right, so our equation for that looks like m1 v1 plus m2 v2 is equal to m1 v1 final plus m2 v2 final. All right, so let's identify our masses. So m1 is Mark, and he is 84 kilograms, and he is originally outside at rest. So 0 meters per second, and we want to solve for his final velocity. So it's a question mark to us. Now M2 is a little hard to identify, but it's actually 0.035 kilograms of gas. And this is also originally at rest. Sorry, that's supposed to be a 2 there. And then its final velocity is 875 meters per second. So let's plug in our information and solve it out. So 84 times 0 plus 0.035 times 0 is equal to 84 times V1F plus 0.035 kilograms times 875 meters per second. So if we do this math out, we're going to find that this is going to be equal to 30.625 kilogram meters per second, and that our initial momentum on this side is equal to 0 kilogram meters per second. And we can use this information in order to solve for Mark's final velocity. And the way that we can do that is saying that this is all stemming from the conservation of momentum. So whatever we are starting with, we need to end with. And again, it's about the products of those things. So we can subtract this from either side. So we can get negative 30.625. Sorry, my pen jumped there a little bit. So negative 30.625 is equal to 84 kilograms times V1F. And you should get a final velocity equal to negative 0.36 meters per second. Okay, the next one is probably my favorite one. So Bumblebee is an Autobot that has a mass of 1,250 kilograms, and it moves down a highway with a velocity of 32 meters per second. It collides head-on with Decepticon Megatron with a mass of 36,000 kilograms, moving at 5 meters per second in the opposite direction. After the collision, the transformers stick together. What is the final velocity of the pair? So this one is really easy to identify. This one is an inelastic collision. So inelastic. And I know that because our masses are sticking together and moving as one. So our equation for this is m1v1 plus m2v2. Again, it all starts the same way, but then our masses combine and we are left with some type of final velocity. Okay, so let's identify which one's m1 and which one is m2. So m1 is equal to 1,250 kilograms. M2 is going to be the Decepticon, and that is 3,600 kilograms. And the initial velocity for Bumblebee is 32 meters per second. And the initial velocity for Megatron is -5 meters per second because they are going in the opposite direction. So I'm going to call Bumblebee moving in this direction as positive. And here, let me rearrange that so it makes more sense. So this is going to be my positive side. So this is going to be Bumblebee, and this is going to be Megatron. This is going to be my negative side. So that's why I'm saying that he's moving towards the negative direction there. And then at some point here, there's going to be a collision. All right, and we want to know what the final velocity for this pair is. So let's go ahead and fill in our information. So 1,250 kilograms times 32 meters per second plus 3,600 kilograms times -5 meters per second is equal to our masses combined times VF, or that velocity final. All right, so now we just do the math. So you should get 40,000 kilogram meters per second here, added to -18,000 kilogram meters per second. And that's going to be equal to our masses combined. So 4,850 kilograms times VF. Okay, so 40,000 minus 18,000 is going to give us an initial momentum of 22,000 kilogram meters per second. And we're going to set that equal to our masses combined times the final velocity of those masses. So now all we have to do is divide both sides by 4,850 kilograms, and that's going to give us the final velocity for our little Bumblebee transformers here. So 22,000 divided by 4,850, and it's going to give us a final velocity of our system as 4.53 meters per second. Okay, so once they combine, they're going to be moving towards the positive direction there. All right, look for my next video on this. I follow through with my idea of going over this, so I go through 4 through 7 in the next video. So I hope this was helpful. Please ask me any questions that you still have, and I'll see you all soon.